All right, perfect. So, all right, so hi everyone, and I'm very excited to be here. I have the honor of being the last speaker today. Yeah, I'll try to keep it hopefully interesting. So the topic, as you can see, will be numerical simulation of CO2 migration in the FluidFlower. And well, I forgot to introduce myself. My name is Lluís. I recently finished my PhD with Professor Ruben Juanes. The work that I will be presenting today is in collaboration with the University of Bergen. And as Winston mentioned, this will be on the FluidFlower, which is a laboratory setup for direct observation of a CO2 migration. And what we will do is show some experiments and then specifically the simulation work that we did using MRST in this project. All right, so with that, the main motivation for this project was that the accuracy and robustness of numerical models of, in this case, geologic CO2 storage are never quantified or almost never quantified with respect to direct observations that provide the ground truth. And the FluidFlower was a laboratory setup that provided us with the opportunity to do precisely that. So that being said, there's some published results in the literature which obviously have performed forecasts based on numerical models of CO2 migration. And one of the things that we have seen in comparison with some available monitoring data from the field is that in this case, these models tend to underestimate subsurface CO2 migration. And for example, in this example that I'm showing here at the bottom, one of the things that was required in order for the numerical models to match the actual extension determined from monitoring data in the field was to recalibrate the models. Otherwise, the forecasts made initially were not very accurate. Another important thing to mention is that there's been some previous benchmark studies which have shown a large number of discrepancies between the forecasts made by different modeling groups. And here you have one example of this. This was a benchmark that was conducted about 10 years ago in a synthetic reservoir. And in this case, the participants were asked to estimate the maximum up-dip extent of the CO2 plume among different things. This is the example that I'm showing here. And essentially what you can see here with different lines, each color representing a different simulation group, is that, well, at the beginning, the forecasts are pretty close, but then as time advances, different groups reported significantly different values. So this study will also serve, well, the study that we conducted and the other studies in the context of the FluidFlower project serve, well, to give an idea of what is the current status in terms of our ability to make forecasts and the things that we will need to improve moving forward. So the specific goals of our study here were, first of all, to evaluate the value of prior knowledge of the system. In this case, we express this in terms of ex situ measurements of the sand's multi-phase flow properties to obtain a accurate or concordant simulation. And what this means is that we will be using 3 different simulation model versions, each calibrated to a different level of local measurements, and we will see how that impacts our ability to history match or calibrate the model. And then as a second goal, we wanted to evaluate also the forecasting capability of our calibrated or history matched numerical models when they are applied to a similar but different setup. Now, here you have an overview of the experimental tanks. In this case, for the experiments that we conducted here and then the simulations that I'm going to be showing, we used 2 different experimental tanks. The smaller one here to the left was used for the history matching. And then the one here to the right, which is larger in dimension, is the main rig that was used to evaluate the forecasting capability. Now, the FluidFlower, just to be clear, when we talk about FluidFlower, we're referring to these experimental rigs. And this would be the main FluidFlower. And then this one, we typically refer to as the medium FluidFlower. Now, these are quasi-2D tanks with transparent panels. We can pour sands from the bottom of the rig to recreate realistic basin geometries, including faults and other structures. And for example, this porous medium here to the right intends to be representative of the structure of subsurface reservoirs in the North Sea. Another thing that the fluid flowers allow, due to the large number of perforations in the back panel in this case, is to represent realistic injection and monitoring strategies. So then in our experiments, essentially we start with the medium fully saturated with water, and then we will be injecting CO2 using two different injectors. Here you have a snapshot in the middle of the CO2 injection for tank A, where we conducted the calibration experiment. This is the smaller or medium fluid flower, and then in the main fluid flower, here you have another snapshot at a point. I think this is after 5 hours, so at the end of CO2 injection, which is the one that we used to evaluate the ability of our numerical models when it comes to making forecasts. So that is a little bit of an overview for the experiments. I think these two snapshots give you a general idea of what we expect to see in terms of CO2 migration, but of course we'll show more details later. And then we did the simulation study using MRST. In this case, as I mentioned earlier, we use 3 different simulation models, each with access to an increasing level of local data. And what this means is that our model 1, we only gave it access to the grain size of the different sands. And then we estimated the rest of the petrophysical parameters that we need for the simulations based on published results in the literature. For model 2, we gave it access to local single phase measurements, that is porosity and permeability, and then we estimated the rest based on the literature. And for the third model, we gave it access to all of the local measurements that were conducted by the FluidFlower team, by the experimental team at the University of Bergen, which includes, in addition, endpoints for relative permeabilities and capillary entry pressures. And here you have an overview of the relative permeabilities and capillary pressure curves. In this case, we used a typical Brooks-Corey curves for relative permeability and capillary pressure. Then a word also on what is our setup in MRST to conduct these simulations. So here we use the ad-blackoil model that many of you will be familiar with. We assigned properties of the water, in this case, to the oleic phase, and then the CO2 rich, the free phase CO2 will be modeled by means of the gas phase. So the gas can dissolve in the water. In addition to the, let's say, base capabilities of black oil model, we implemented a number of additions in this case, which include the calculation of PVT properties using a thermodynamic model. I think this was mentioned in passing by one of the talks earlier. The model that we implemented here is the one by Spitzer and Prues from 2003 and 2005, which is detailed in this paper, specifically the implementation for black oil models. We also implemented relative permeability hysteresis and molecular diffusion to better match the experiments. And here what I want to mention is that these specific 3 points, these additions are already available on GitHub because they are part of my PhD thesis. But right now I will be working with MRST developers in order to integrate these or the aspects that are most useful, at least, into MRST. So some of these capabilities should be available by default in MRST in the future. Now, yeah, there will be a paper specifically focused on these additions coming out hopefully soon. But today the focus is not necessarily the setup, but rather the application that we did. Now, for the history matching, I just wanted to mention the overall process that we followed here. So we compared areas in different locations of our experimental rig and simulation model at different times. So those are direct observations from the experiments, which were compared with the simulation results. And then also we tracked the time of sinking of convecting fingers, which, excuse me, which was also matched to the numerical models. So here you have an overview of the initial simulation results. And these are the results after the first simulation that we did with each of models. So that is at the beginning of the calibration or history matching process. And one can already see that comparing with snapshots at different times with the experiment and then the 3D simulation models, model 3, which had access to all local measurements, is already significantly closer to the distribution that we see in the experiments. Here you have an overview of the calibration process. What I'm showing in this slide are 3 concordance plots obtained for model 1, model 2, and model 3. And there are essentially 2 things that I want you to notice in this figure. So first of all, model 3 was already, for all the different aerial quantities that we used for history matching, was already pretty close to the experiment from the beginning. The initial simulation is the one that you see with smaller data points, and most of them are already very close to the black line in this case, which indicates perfect match between the experiments and the simulations. And then also this model was calibrated with only 7 iterations compared, for example, to model 1, where we required 11 iterations for successful calibration. The other thing to mention is that at the end of the calibration process, all of our 3 models achieved very good concordance. And in this case, this is quantified by this concordance correlation coefficient with values above 0.99. All right, so now I'm going to show you an overview comparing in this case the calibration experiment with the simulation results after calibration for one of the models. Basically, you can see the CO2 migration in the lower injection reservoir after injecting in the first injector around here, and then injection in the second injection point, essentially, and then accumulation of the CO2 below the main top seal, which prevents migration to the surface. So one of the things that you can see here is that qualitatively the match is pretty good. But there are some areas where there's already some differences, such as faster sinking of the brine in this area. So now one of the key questions is, okay, so after this calibration process, how are our models going to perform when we apply them to a similar but different setup? And this is what we're trying to show in this slide. So in this case, we're comparing different snapshots as well of the experimental results in the main FluidFlower with our modeling results for model 1, model 2, and model 3 in this main FluidFlower. And so you can see that overall, the CO2 migration is qualitatively speaking very similar between the different models and the experiment. But there is one area in particular here in the upper left where model 1 in this case is doing significantly better than model 2 and also model 3. Now, the reason for that mainly is that here we have a very heterogeneous fault zone, which was, well, very difficult to model deterministically. And so as a result of that, our forecasts with the calibrated models didn't perform as good as we had expected, particularly for model 2 and model 3. So, yeah, the other thing to mention here is that, of course, we did a detailed quantitative analysis of all of these results, which I'm not going to show today for reasons of time. But the main sort of takeaway from this analysis, particularly the forecasting part of the study, is that accurate deterministic forecasts are very difficult to obtain. I apologize for stopping every minute or so to just take a sip, but I'm currently sort of in the medium fighting a cold, so I can't speak consistently for long. But luckily we're getting close to the end of of the presentation. And basically, I want to close with 2 slides with some conclusions and recommendations. Now, the first 2 conclusions are that the time required for history matching in Model 3 was significantly lower than Model 2 and Model 1. So then, qualitatively speaking, our calibrated simulation models achieved satisfactory concordance throughout the experiments. Forecasts with calibrated Model 3 were less concordant than those made with measured values. This is something that I didn't detail in this presentation, but essentially what it means is that for the second experiment and simulations in this setup, we run a simulation with the initial parameter values and then another one with the parameters after calibration. And for the Model 3, which had access to local data, the overall concordance between the experiments and simulations was better with initial parameter values. That was somewhat surprising, but what it emphasizes is the importance of local measurements and history matching in the same geologic setting. And then simulations without dispersion cannot approximate, in this case, this is hydrodynamic dispersion that I'm referring to, cannot approximate the compact CO2-rich sinking front that is closely trailing the convective fingers in our experiments. And well, after reaching these results and conclusions, one can reach naturally a set of recommendations, in this case directed to forecasts with numerical models applied to subsurface CO2 migration. In this case, confidence can be increased by obtaining local data, quantifying petrophysical parameter uncertainty, testing sensitivity to petrophysical parameters in different model regions, using historical data from the same geologic setting, including post-injection data, and incorporating multiple scenarios of CO2 migration. So in case someone is interested in knowing more details, the paper was recently published, so you can check all the analysis there. And I think I'm right on time to close now, and I'll pass the word to Øystein. Thank you.